Okay. So in my talk, I will introduce multiple peculiar neutron stars and their tangled magnetic fields. And I explain how we try to model these objects. So I will start with simple magnetic field configurations and slowly increase complexity, going to stochastic magnetic field and Taylor-Sprout dynamos eventually. If I have time at the end, I will talk a little bit about ambipolar diffusion in the core of neutron stars. So first, a few words about neutron stars. As you, of course, know, neutron stars are compact remnants of supernova explosions. A typical size would be like 10 kilometers, and the typical mass would be 1.4 solar masses. It could be a bit more, could be 2 solar masses. What neutron stars are especially famous for are their magnetic fields. Magnetic fields of neutron stars could go from 10 to the 8 Gauss to 10 to the 14 Gauss. Or I have a problem with this pointer, if you can help me, because it's appearing and disappearing. And neutron stars, they rotate really fast. For millisecond pulsars, you could expect rotational periods like 2 milliseconds. And for some neutron stars, you get easily rotational periods of 25 seconds. If it is accreting neutron stars, you get periods of hours. This thing in neutron star science or in pulsar science is, I think it nearly works. Okay. For isolated neutron stars, two main characteristics which are always measured or nearly always measured are spin period and time derivative of the spin period, so how fast the spin is increasing. Spin in isolated neutron stars is increasing because normally they have some kind of dipolar magnetic field, poloidal one, and these accelerate particles and emit electromagnetic radiation. So slowly over time, a neutron star would move from somewhere here, where it is born, to somewhere here, where it stops being detectable. If I'm talking about normal radio pulsars, for example. Most of objects here, this dark cloud here, are normal radio pulsars. Objects here are millisecond pulsars. So because spin periods of neutron stars are increasing over time, you can say something about their magnetic fields. This estimate works even if you perform detailed MHD simulations. There is a numerical factor here. And most magnetized neutron stars are located in the top right corner. This could be called magnetars. If you see some of these numbers here, it's 10 to the 14 Gauss, and this is 10 to the 12 Gauss, which is typical magnetic field of a radio pulsar. These neutron stars are weakly magnetized, at least outside for an external observer. If you can only measure dipolar magnetic field, you would say what this object would have magnetic fields of 10 to the 8 Gauss. But neutron stars are really complex, and here is a brief classification. If you want to learn more, you can read one of these reviews on so-called neutron star zoo. So most people know about radio pulsars. Magnetars are actually a block of things. So some magnetars are anomalous X-ray pulsars, some are soft gamma repeaters, and some are OOB magnetars. Another type of neutron stars you might encounter are central compact objects. A few of them you see here. It's CCOs. They are found in the center of supernova remnant. But you get a small estimate of magnetic field. There is no radio emission. It's only thermal emission. There are also XDIMs, or X-ray dim isolated neutron star. They are located here. And it's thought that they are produced from magnetars because magnetic field evolve over time, and magnetars would end up somewhere in this region. And as I mentioned, there are millisecond pulsars way here. So I will go through some of these classes in slightly more details. So as I say, magnetars are not a single observational class. First, they were discovered as anomalous X-ray pulsars. So their X-ray properties are very similar to accreting neutron stars in, for example, high-mass X-ray binaries or low-mass X-ray binaries. But there is no star from which it could accrete. So there is no place from which this neutron star can extract material. It just shines in X-ray. There are soft gamma repeaters, so they emit soft gamma rays occasionally. Eventually, both these classes were combined into a single class because soft gamma bursts were detected from some of the anomalous X-ray pulsars. And with better X-ray telescopes, some of the soft gamma repeaters were recognized as anomalous X-ray pulsars. There is still a little bit of historical division, and not from every soft gamma repeater we see this type of X-ray emission, which would correspond to anomalous X-ray pulsar. And a separate part of magnetars are low B magnetars. Some of them are anomalous X-ray pulsars, I believe. So these are magnetars which show bursts and outbursts. So they show a kind of transient behavior typical for magnetars, but their magnetic fields, they are weaker than this value 4 multiplied to 10 to the 13 Gauss. So it was a little bit unclear why they are magnetars. So another peculiar property of magnetars were thermal emission. So if you divide X-ray luminosity of a magnetar by value of rotational budget available for this neutron star, these are slowly rotating neutron stars, you get values comparable to 100%. In some cases, you will get more than 100%. So it should be additional source of energy for magnetars to shine in X-ray. And it is believed that the source of energy available to magnetars is their hidden magnetic field, mostly toroidal, because in some cases it's not enough to have a poloidal dipolar magnetic field, and you need to have a stronger magnetic field somewhere in the crust to explain this. It's a similar story for dim X-ray isolated neutron stars, which are located somewhere here. They are a bit weaker in X-ray, but their rotational budget is not much bigger. So if you observe a typical radio pulsar in X-ray, some of them you can see in X-ray, their X-ray luminosity would be 1% or a fraction of percent of their spin-down luminosity. For magnetars, this is not the case. So yeah, as I said, X-ray dim isolated neutron stars are located in this region. People looked at X-ray dim isolated neutron stars in details, and these are phase resolve spectroscopy. So this is the rotational phase of the neutron star, and this is X-ray energy. These are really soft X-ray below, so it's 1.4 kilo electron volt, and this is 0.4 kilo electron volt. Their X-ray emission is mostly black body. It could be a composition of two black bodies. But on some objects, like these two objects, you see these features, or dark features, better to say, which always stay in the same rotational phase. And it is believed that these features are explained by scattering of X-ray radiations by protons. So it's cyclotron resonance scattering in localized loops of magnetic field. And magnetic field in this case would correspond a value which is comparable to spin-down magnetic field, but a bit stronger, so 5 times is just a little bit stronger. So it means that you don't just have a regular dipolar magnetic field, but you also have isolated loops of magnetic fields on surface somewhere, for example, here at the phase 0.5. In these two sources. A similar picture is seen as for low B magnetars, but for low B magnetars, the difference between this arc of magnetic field or individual loop of magnetic field and dipolar magnetic field could be 100 times and not just 5 times as in dim isolated X-ray neutron stars. So central compact objects, as I said, there are a few neutron stars which I discovered in the center of supernova remnant or very close to the center of supernova remnant. We don't see any radio emission from these neutron stars. So they are not radio pulsars, but we see X-ray emission. And in certain cases, X-ray emission varies with time. So you can estimate spin period and spin period derivative. And these spin periods are typical for radio pulsars. It could be 500 milliseconds or half a second. Period derivatives are a bit weaker, so magnetic fields would be 10 to the 10 Gauss, which is a bit unusual for radio pulsars. And again, there is no radio emissions in this case. You have a pulse fraction of 9–11% in certain cases. In one case, it's 64%. So this particular object has a huge pulse fraction. Again, thermal emission from central compact objects is a bit more than you would expect based on neutron star cooling. So it is thought that they have strong magnetic field hidden, one in the crust, possibly multipolar magnetic field. So if I go next to millisecond radio pulsars, probably you've seen this figure. An X-ray telescope NICER was launched to measure radius and masses of millisecond radio pulsars, at least a few of them. And this was the first, basically, test millisecond pulsars for which these things were measured really carefully. It's J0030 plus 0451. What you see in this case, you see again this phase resolve spectroscopy. So here is energy of individual X-ray photons received by a telescope, and here is the rotational phase. So you see there are certain features on a surface. So the surface of this neutron star does not emit the same way everywhere, but instead there are certain hot spots and there are certain cold spots. Really, and people behind this work, they estimated location and size of these hotspots. In this particular case, they are located in both of these hotspots are located in the same hemisphere. One of them is more similar to a dot, and another is a long arc. So this hotspot would correspond to magnetic field structure near the surface of the neutron star. It's a place where currents hit the neutron star surface, and it becomes hot and emit in X-ray. So if you have a location of radial magnetic field, strong radial magnetic field here, and strong radial magnetic field in this arc, you start thinking maybe it's not dipolar. Maybe it's something much more complicated. And some of people here, Bilos and Kalopartakos, suggested that it's a combination of dipolar and quadrupolar magnetic field. The problem is that millisecond pulsars are really old objects. They lived for giga-years, and you normally would not expect their magnetic field to be that complicated. So from observational evidence, we have this. This is a kind of first take-home message. Magnetic fields of neutron stars are very complicated. It's not just a dipole. There are small-scale features. There are possibly toroidal magnetic fields. And in some cases, you might have dipole or quadrupole combined. So it means that we need to understand how such magnetic fields are formed and what is their evolution. And it could tell us a lot about structure of the neutron star. As for the neutron star structure, it is thought that the outer approximately kilometer, a shell with a depth of kilometer, is a neutron star crust. It is solid. So protons and neutrons in the crust, they are not moving. Electrons can be moving, so it's a bit like a crystalline structure. And if you go deeper inside a neutron star, you might have outer and inner core. Inner core is expected to be inside the most massive neutron stars. And it could be an exotic neutron star core. We don't really know exact composition of the inner core. So, but I'm saying that if you have a strong magnetic fields, they would connect deeper regions of the neutron star to the surface, and they would produce hot spots at the surface. So using X-ray telescopes and using diversity of the neutron star, you can say something about structure of magnetic field and possibly structure of the neutron star inside. which is my ultimate goal, to understand, to connect structures of magnetic field inside the neutron star core, crust, with hot spots and their observations in X-ray, and possibly also with gravitational wave telescopes, because strong magnetic field, they gonna deform the neutron star core and neutron star crust, and so neutron stars start emit gravitational waves. So now I would like to tell you more about magnetic fields of neutron stars and how they are formed. Basically, there are two main hypotheses, fossil field hypothesis and dynamo hypothesis. Fossil field says that some massive stars, like 5–7% of massive stars, B stars, they are strongly magnetized. They have a magnetic field at the top of the atmosphere comparable to kilogauss, 10 kilogauss. And if you continue with strong magnetic field deep into the core of this star, you will get magnetic fields which are a few orders of magnitude stronger. If you collapse this core, forming a neutron star, you will get a magnetic field comparable to magnetars in certain cases. Of course, fossil field hypothesis assumes that there is no motion during the collapse. So magnetic field is frozen and collapse proceeds relatively smoothly. This is not the case, as we know. Supernova explosion is extremely turbulent process, and core could be showing a lot of turbulence caused by different neutrino emissivity or by fallback. So these are some older simulations by Nagakura, 2019, and he shows orthogonal velocities of the neutrons of the material in the proto-neutron star. So red here would correspond to large velocities orthogonal to the radius of neutron star. And there are two regions where these velocities are developed. One region would correspond to classical convection in proto-neutron star, and another region would correspond to fallback. So fallback is when material during the supernova explosion doesn't have enough energy, and some of it returns back to the proto-neutron star, changing angular momentum and causing shear in the neutron star. So now, when we know all of this, I would like to tell you how we model magnetic field evolution in neutron stars. In first part of my work, I'm modeling crust-confined evolution. It means that magnetic field is only present in the crust. And in the crust, magnetic field evolution is only governed by Hall evolution and ohmic decay. I would also remind for some of you what are poloidal-toroidal decomposition, because I will mention poloidal and toroidal flows and magnetic fields a lot. So poloidal is in this direction, so it's usually north-south kind of direction, and toroidal is this direction. So if you think about axial symmetry, toroidal would be azimuthal magnetic field, for example. So we solve magnetic field evolution as well as thermal diffusion equation in the crust of neutron star using code called parody. It's a spectral code, so we expand magnetic field into spherical harmonics at each radius within the crust, and it's a finite difference in radial direction. These are two equations which we are solving. There are many terms here, so I will slowly go through different terms and introduce their importance. Magnetic induction equation has three terms here. Last term is ohmic term. Magnetic field naturally decays in the crust because crust has certain conductivity, so currents decay over time. Hall term is the most interesting term. It's a nonlinear term and connects large-scale magnetic field with small-scale magnetic fields, as well as poloidal with toroidal magnetic field. Biermann battery is normally quite small in our simulations, But if you would induce a strong thermal gradient inside the neutron star crust, you might generate magnetic field. The reason for this is what heat is transported by electrons, and of course electric current is also transported by electrons. So if for some reasons electrons have to transport a lot of heat, they might create additional currents, which would create additional magnetic fields. So some terms here translate to terms into thermal diffusion equation. For example, ohmic term, heat is released because current decays. And of course, Biermann battery term works for temperature as well. If you have certain magnetic field configuration, it can cool down certain parts of the neutron star crust. And the most tricky term, even though it might be surprising, is the thermal diffusion term. Again, heat is transported easily along the magnetic field lines because it is transported by electrons. So diffusion is most efficient in direction along the magnetic field lines and is inhibited in direction orthogonal to the magnetic field lines. Here is a set of boundary conditions. So on the top of the neutron star crust, we assume force free. Essentially, it's vacuum. So we assume what any kind of heat which reaches surface of the neutron star is emitted as black body radiation. There is a really thin layer on top of the neutron star crust. It's called thermal blanket. This layer, where temperature drops by 2 orders of magnitude. A typical temperature inside the neutron star core would be 10 to the 8, or maybe if it is an old neutron star, it could be 10 to the 7. But surface temperatures are more comparable to 10 to the 6, 10 to the 5. To solve properly for this layer, we would need a lot of resolution. That's why people solved this problem before and introduced the parameterization, how temperatures in deeper layers of the neutron star are connected to temperatures on the surface of the neutron star. And we use this parameterization as our boundary condition. So in this part of my work, as I say, I assume there is no magnetic field in the core, and core is not cooling. So the second one could be adapted if I choose a different temperature of the core. And for Meissner condition, I will talk about it more at the end of my talk. So what would happen if you start with a really simple magnetic field configuration, a configuration which everybody had in mind, maybe like 20, 30 years ago. So just a dipole. There is no toroidal magnetic field. It's a dipolar poloidal magnetic field with small perturbations to break initial axial symmetry and see if this configuration is stable or not. Well, essentially it's stable. Nothing develops much in this direction. What you see is the equator gets really hot. There are two reasons for this. First reason is equator gets isolated from the core. Magnetic field is not radial around equator in the crust. And second reason is it is a place where most currents are located. So currents decay, a lot of heat is released, equator becomes hot, poles becomes cold. If you increase magnetic field even more, you see a very similar structure. Equator gets even more hot and poles get approximately to the same temperature. So poles here are thermally connected to the core. Whatever temperature would be in the core, it would correspond to temperatures at poles translated through this condition of 2 orders of magnitude smaller approximately. So now I mentioned toroidal magnetic field in magnetars, and people on observational side of the communities were saying what magnetic field should be at least 50% toroidal or 90% toroidal. So here I designed different initial conditions. It's still quite simple. It's still a dipole with some large-scale toroidal magnetic field in the crust, which has half of the magnetic energy. So over time, over 10 kiloyears, this magnetic equator shifts towards the northern hemisphere. It all depends on orientation of the toroidal magnetic field. If you choose a different orientation of the toroidal magnetic field, your equator would shift toward the southern hemisphere. But otherwise, the picture is relatively similar. So you still have a hot equator. So equator is shifted now towards the southern part. So this is a mistake. It should be 10 to the 6 Kelvin, not 10 to the 8. And a large area is hot around the equator. You can try to rotate this neutron star. Of course, you can choose rotational axis arbitrarily. But if you think, if you see hemisphere of this neutron star, you don't expect much variability. And if you think about a real neutron star, you would see more than a half of the hemisphere. So we started to think what can we do differently to make it more variable in X-ray. So this initial condition is artificial, but quite interesting. So in this case, we still have dipolar magnetic field, but we misalign toroidal orientation of the toroidal magnetic field in the crust by 45 degrees. And in this case, we started to see some structure. So it's a general feature. As soon as you get around 90% of toroidal, you get some instabilities. So you will get some kind of filaments in magnetic field. They are not super noticeable. I don't think you would see them in X-ray observations, maybe through scattering in individual loops. But what is interesting about this particular configuration is what if you start to rotate this configuration, occasionally you see a hot hemisphere and sometimes you see cold hemisphere. So this might produce a large variability in X-ray. So we thought, how can we compare something like this with X-ray observations by Gotthelf of a magnetar in quiescence. So there is a hope what we see here in X-ray is actually emission produced really close to the surface of the neutron star, hopefully in the atmosphere of the neutron star. So this should be comparable to what we are producing in our magneto-thermal simulations. And how we do it? Well, using a code. If you have a hot spot, it emits many more photons. We propagate in a curved time space. We used analytical equations from article by Bill-Barodov. And when we integrate over the whole visible hemisphere of a neutron star, there are two axes involved in this problem. One axis is the rotational axis of the neutron star. Another axis is the orientation of original dipolar magnetic field. So why we need this second axis is because we have our thermal map, and we need to compare how we put this thermal map on rotational axis of the neutron star. So rotational axis can be anywhere within this thermal map, essentially. So this is a simple example. If we run analysis like I explained a few seconds ago, we get a light curve like this for different orientations of two angles. Now we can compare it with individual X-ray observations of magnetars in the quiescence. And it seemed that in some cases we were successful. For example, as in this case of soft gamma repeater, our model is black curve and X-ray observations are shown with error bars here. What is striking about this particular soft gamma repeater is what light curve is not symmetric around the peak. If light curve is symmetric around the peak, like in this anomalous X-ray pulsar, there are many configurations which can produce this type of light curve. Basically, you put a hot spot and you will get some kind of sinusoidal light curve. But if light curve is not symmetric around its maxima, it's much harder to produce. So it was really reassuring for us what our misaligned configuration for poloidal and toroidal magnetic field produced with non-symmetric light curve, and it coincided with some of the observations. Of course, there are observations of magnetars which we cannot describe. For example, these two sources. As you can see, there are deep structures here. They might be related to additional absorption in magnetosphere, because it's really hard to produce these deep structures with just hot spots on the neutron star surface. And this would be one of the directions for future investigations. So now I explained you. Do you have a question?
A quick question.
Yeah.
So for your treatment, you do not seem to have considered GR effect, except Andrei paper. So
yeah.
Is it? I mean, and you are able to explain observation also. So I'm just a little curious.
Mm-hmm. So we used a general relativity effect for light propagation, because it's important. Light is really curved by time space here, but we didn't use general relativistic effects for solving our magnetic induction equation. This is true. But some other group by points they showed what a difference for magnetic field is not as large, and it's a matter for future investigation for us to see how much relativistic effects would change magnetic field.
It might not introduce too much effect. Error may not be too much if you go with Newtonian calculation for even interior structure.
For magnetic field evolution, for certain things it is very important. So okay, I explained to you large scale magnetic field configuration, so configuration which you would use if you read textbooks about pulsars, for example. But now what if magnetic field configuration is on other side of the spectra? What if you are having a magnetic field configuration which is really small scale? For example, it has spherical harmonics with a size of 10 or 15 or 20, and you put them randomly, so you have multiple poles, north and southern poles. You run simulations and you get a thermal map like this. So there are hot regions, there are cold regions. But now if you start to rotate this type of surface thermal map, you won't get much variation. It's within a few %, because you always see multiple hot regions and multiple cold regions at every orientation of this neutron star. So we think what this might be comparable to central compact objects, because you still have strong magnetic fields, you still have really hot spots, but you don't see much variation beside a few %. And another theoretical direction which we can pursue, we can shift location of our dipole toward one of the hemispheres. So it's off-center dipole. This idea was discussed in a neutron star community for a long time. So essentially, it looks like one hemisphere is more magnetized than another hemisphere, or at least one pole is much smaller physically than another pole. So what we noticed in these simulations, it is what this degree of off-center decreases over time. Magnetic field configuration becomes more centered dipole over time, but otherwise we see all the similar structures. So to some extent, off-center dipole configuration could mimic properties of poloidal plus toroidal magnetic field in terms of thermal maps. But of course, you won't get as much toroidal magnetic field. We didn't put any toroidal magnetic field in these configurations. So now what would happen if we start thinking about simulations of supernova explosions? I talked to a French group and they modeled Tyler-Sprout dynamo. Tyler-Sprout dynamo is when you have a fullback. So you have a proto-neutron star here. It's seconds within the supernova explosion. Some of the material returns back. and it returns with different angular momentum. One of the reasons why it could have different angular momentum because neutron star has a NATO kick, so it moved within the supernova remnant. So material is accreted with different angular momentum. So it produces a shear, and if you have some weak magnetic field, it can be sheared. So you produce a lot of azimuthal or a lot of toroidal magnetic field at this stage. This toroidal magnetic field becomes unstable because of Tyler instability. It forms poloidal magnetic field, arcs of poloidal magnetic field. Do you have a question? Yeah?
What is the time scale for?
Yeah, for this time scale, it's seconds during the supernova explosion. So, yeah, these are like 10 seconds maybe, like really seconds during the explosion. It's a proto-neutron star. You form some poloidal magnetic field, arc of small scale poloidal magnetic field, which gets sheared again, and you get some additional toroidal magnetic field. So this process could repeat a few times, and you end up with a configuration with a strong toroidal magnetic field with individual arcs of poloidal magnetic field. And in observations, it's really something we would hope for, because arcs might produce these scattering features in phase resolved spectroscopy, while toroidal magnetic field might be a field which hits the crust of the neutron star and is responsible for some of the magnetar properties. So Barrère, Gillet, Reynaud, and Rebul-Zalce in 2023 they modeled this scenario using Boussinesq approximation. So on the left side of the slide, we see a magnetic field which they produced. So it's really concentrated toward poles. It's really toroidal, so you rotate multiple times around the rotational axis with little bit of poloidal magnetic field. You don't have much magnetic field anywhere here at all. We translated this magnetic field into our simulations, so only to crust. And in our initial condition, we see a very similar structure as expected. So most of the magnetic field is toroidal, and it's concentrated toward the pole. So we kept angular structure exactly the same up to 60 spherical harmonics, but we slightly modified the radial structure of the magnetic field to satisfy our boundary conditions. And now it's interesting what this type of initial condition, which was never studied in neutron stars, could mean for a neutron star. So we ran our simulations for 200 kiloyears. First thing which we notice is what poloidal magnetic field stays relatively weak. We start with something like 10 to the 12 Gauss. It's a dipolar poloidal magnetic field, so this is a field which would be responsible for slowing down of the neutron star. And it still stays weak through most of the simulations. It grows a factor of 2 here. If you think about quadrupole, this is the second moment, and it could also contribute to the slowing down of the neutron star. It grows maybe 3 times, but it's also comparable to 10 to the 12 Gauss. So dynamically, you would estimate magnetic field of this neutron star as something multiplied to 10 to the 12 Gauss. But if you look really close, you see individual arcs of magnetic field with a size less than a size of the neutron star. And the strength at the footprints of these arcs is much, much stronger. It could reach 10 to the 14 Gauss in certain places. And this is more similar to solar physics. So on the sun, the general dipolar magnetic field is comparable to 1 Gauss. But if you look at individual spots, you get magnetic fields comparable to kilogauss, so 3 orders of magnitude stronger. So similarly here, a regular large-scale dipole is around 10 to the 12, individual arcs of magnetic field comparable to 10 to the 14 Gauss. If you would think about currents in magnetosphere, our very preliminary and rough treatment of currents would say you what strongest radio currents would coincide with the strongest radio magnetic field. So the regions with strongest radiomagnetic field would be heated the most by current. So you would produce a few very small individual hotspots, which more or less comparable to what is seen in observations of low B magnetars. Now, if you would think, is it a magnetar still? Like, we have small magnetic field, we have some toroidal magnetic field, but would it make it a magnetar? So these days, magnetars observationally classified as neutron stars with a lot of transient behavior, bursts, outbursts. One of the models describing bursts and outbursts of magnetars was suggested by Lander and Gorgouliatos, 2019. So you could estimate contribution of magnetic field to the pressure at the beginning of your simulation at some time after. Of course, magnetic field decays and moves, evolves, so contribution becomes much weaker over time. So you would form a region which is prone to failing, and this region could cause some kind of outburst behavior in magnetars. So we found this region in our simulation. So it means what potentially, if we understand physics of outbursts of magnetars correctly, it could be a magnetar. A tricky point for this model is period, because neutron stars, magnetars, they have spin periods of 10 seconds. But if this is born with a normal spin period of radio pulsar, like half of a second, this would be far away from 10 seconds, and magnetic field of 10 to the 12 is definitely not enough to slow down this object until 10 seconds spin period. So we thought what still it's Tyler-Sprout dynamo. So there is some fallback already in this model. Can we think about continuation of this fallback in a form of fallback disk? And we modeled using model by Ronchi, Ria, and Graber, and more earlier version by Comperz, interaction of dipolar magnetosphere with fallback disk. And we see what we can get spin periods comparable to 10 seconds in 100 or 200 kiloyears. So if this fallback disk exists and interact with magnetosphere, it can slow down this object to rotational period comparable to ones, which are typical for low B magnetars. Of course, this disk would be depleted at some point. We don't know exact mechanism, but if it is depleted, your magnetar can end up in this region. So top lines would be describing most efficient slowing down by fallback disk, while the lower line would describe just dipolar electromagnetic spin down of the neutron star. And we see what all the low B magnetars are located within this region, as well as some long period pulsars. So in this sense, our model predict period derivative for these objects. So these are my first conclusions for crust confined configurations. I have 5 minutes. Okay, maybe I will finish here in this case. Simulations of the crust-confined magneto-thermal evolution is in good quantitative and qualitative agreement with modern observations of magnetars and quiescence. Stochastic magnetic field configuration, so small-scale magnetic field configuration, could describe general compact objects. If you think about more realistic simulations of supernova explosion when just assuming dipolar magnetic field, if you think about Tyler-Sprout dynamo, for example, this is a configuration which creates strong toroidal magnetic field and weak dipolar toroidal, but patches of extremely strong radial magnetic field, which could be responsible for heating of the surface by currents. And this type of magnetic field configuration could lead to magnetic outbursts if our models are correct. So we think what objects produced with Tyler-Sprout dynamo were quite similar to low B magnetars. So, and these findings suggest that there might be multiple formation channels for classical magnetars and for OB magnetars, because we reproduce OB magnetar with Tyler-Sprout, but we cannot reproduce classical magnetar at the moment. So if I don't have any more time, thank you very much for your attention.